Hello and welcome to Algebra. Today we're going to learn about simplifying radicals. Okay, so before we start simplifying radicals, there's some vocab words you need to know. All right, and the first one is a prime numbers. So prime numbers you start learning back in like elementary school. All right, so a prime number is any whole number that's greater than 1 whose factors are 1 and itself. So what are some prime numbers? Well, 2 is a prime number because it can only be divided by 2 and 1. What's another one? Let's say like 7. 7 is a prime number because 7 can only be divided by 7 and itself. Nothing else can divide into it evenly, right? What's another one? 3 is a prime number. 5 is a prime number. 11, right? So all these are prime numbers, and prime numbers means they can only be divided by itself and 1. Okay? Composite numbers are a whole number that can be divided evenly by numbers other than 1 in itself. So that means it's numbers that you can divide something else into. So like 6, because 6 can be divided by 2. It can be divided by 3, right? 12 can be divided by 2. It can be divided by 6. It can be divided by 3. It can be divided by 4, right? So these composite numbers are numbers that you can break down more. Right? So prime we can't break down anymore. Composite we can say something times something else will get you that number. Right? Factors, numbers you can multiply together to get another number. So list the factors of 20. All right, so for 20 we could do 1 times 20, right? 1 times 20 would get us 20. 2 times 10 would give us 20, right? What else would give us 20? 4 times 5 could give us 20, right? So these are our factors of 20. 1, 2, 4, 5, 10, 20, right? So when we're simplifying radicals, we need to know what a prime number is, a composite number is, and we need to know what factors are because we're going to make factor trees, right? So we can simplify all radicals by making a factor tree, right? We must continue to expand our tree until there are no composite numbers left. We want to look, on our factor tree, we're going to look for pairs, right? And pairs are going to go on the outside of the radical because they were perfect squares. And non-pairs are going to stay inside the radical, right? And you'll see what I mean by that in a second, all right? So we're going to make factor trees, and we're going to keep factoring until there's no more composite numbers. And we're going to look for pairs. And those pairs we can pull outside the radical. Anything that does not have a pair is going to stay under the radical. All right, let's see what I mean by that. All right, so I have 20, right? 20. I can make a factor tree of 20. So I say to myself, what times what gives me 20? Well, I know 4 times 5 gives me 20, right? 4 times 5 gives me 20. 5 is a prime number. I can't break that down anymore. But 4 I can break down more, right? 4, I know 2 times 2 will give me 4. So 2 is a prime number. I can't break that down anymore. Right? So what are my prime numbers that are here? Well, my prime numbers are 2, 2, and 5, right? So what I can do is I'm going to rewrite those underneath the radical. So I can rewrite it 2 times 2 times 5. I'm going to put those underneath my radical. And I put it up here because 2 times 2 gives me 4. 4 times 2 gives me 5. Sorry, 4 times 5 gives me 20. And 20 is my original number, right? So that's an easy way to check to make sure you got all your prime numbers. If you multiply all your prime numbers together, you get that original number. All right, so what I want to do now is I want to look for pairs. So I'm going to say, all right, what pairs of numbers do I have? Well, I have a pair of 2's, right? So since I have that pair of 2's, I can take that outside the radical. And I'm going to take that outside by writing a 2. I took out a pair of 2's. All right, so what didn't have a pair? Well, 5 did not have a pair, so that's going to stay inside the radical. And this is my answer. This is my simplified radical. All right? So you might think to yourself, why do I only write 1, 2 when I'm pulling out two 2's pretty much, right? I'm pulling out a pair of 2's. Why do I only write 1? Okay, so the reason why we do that is look up here on this example. 2 times 2. What is 2 times 2? Well, 2 times 2 is 4, right? And this is a square root sign, right? So what is the square root of 4? Well, the square root of 4 is 2. So to pull it outside the radical, I got to find the square root of that. So basically 4 is a perfect square, that I'm pulling out from underneath the radical. All right, let's do this one right below it. This one right below it has a 5 in front, and we're going to get to that in a second. But first, I got to break down what's inside the radical, what's under the radical. So I have 128. I'm going to break that down. So what times what will give me 128? Well, I see it's even, so I know I can divide it by 2, right? 64. So 2 times 64 would get me 128. All right, 2 is a prime number. I can't break that down anymore. 64 I can break down though. 64 I can break down. What times what gives me 64? 8 does. 8 times 8 gives me 64, right? And 8 I can break down more. I can break down into 4 times 2, right? And then 4 I can break down even more into 2 times 2. And I'm going to do the same thing for this 8, right? It's going to be the exact same. 4 times 2, and then 4 we can break down into 2 times 2. So now I want to rewrite this with everything underneath. So I have this 5 in front, so I don't want to forget about that. So I'm going to put the 5 in front, and then I'm going to put my radical, and then I'm going to write all my prime numbers underneath that radical. Right, so what are my prime numbers? Well, I have 2, 2, 2, 2, 2, 2, 2. How many 2s is that? 1, 2, 3, 4, 5, 6, 7 2s. So I got 2 times 2 times 2 times 2. 1, 2, 3, 4 times 2, 5 times 2, 6 times 2, 7. Woo, that's a lot of 2s. All right, so now I'm going to look underneath my radical, and I'm going to pull out my pairs of 2s. So I see I have one pair of 2s here, right? I see I have another pair of 2s here, and I have another pair of 2s here. So I'm going to pull all these out here to join up with that 5. I'm pulling those outside the radical now. All right, so let's rewrite it. So I have 5. All right, and then I pulled out a group of 2, and I pulled out another group of 2, and I pulled out another group of 2. All right, so what's left inside the radical? Well, I have 1, 2 here that did not have a match, so that's going to stay inside the radical, right? And on the outside of the radical, I can multiply all these things together. All right, so 2 times 2 is 4, 4 times 2 is 8, 8 times 5 is 40, so it'd be 40 square root 2. And that's my final answer. I can't simplify that anymore. All right, so a good way to check yourself and check your work is to use Desmos or use a calculator, and you can check your work. So let's check this first one. I have square root of 20. So if I type in square root of 20, that gives me a big long decimal like that, right? That's why we simplify it, because this is an exact answer, whereas this, we can't get an exact answer because this decimal goes on forever. But I can check my work by typing in this right here. I can do 2 square root 5, and I should get that same exact decimal, which I do, right? Okay, so same thing the other one. My original one here was 5 square root 128, right? So what's my new one? I have 40 square root 2. And look at that. I got the exact same decimal, so I know I got it right. Okay, so Desmos is a great way to check your work to see if you got it correct or not, all right? All right, so go ahead, try these two on your own. Try these two on your own. Use the factor tree, write them underneath, pull them out. All right, so go ahead, pause it, try those two on your own. Unpause it when you're done, and we'll go on to the next thing. Okay, so what happens, what if it gives us the answer and we have to figure out the original problem? Like this is what we just simplified stuff to, something that looked like this, right? So what if they give us this and they say, what's the original problem? So what would I do there? Well, remember 3 was allowed to leave the party because it started out as a pair. Originally 3 was at the party or inside the radical as 9, right? Because 2 3s will go back inside. So it'd be 3 times 3, which is 9, right? And the square root of 9 is 3, so that's why we could pull it out. But the 5 was not allowed to leave the party because it didn't have a pair. So that 5 has stayed trapped inside. So if I'm going back to my original problem, this 3 has to go back inside my radical, right? And to go back inside, I have to have 2 3s, because remember I pulled out a pair of 3s, right? So then I can multiply these together and figure out my original problem. 3 times 3 is 9. 9 times 5 is 45. So my original problem was square root of 45. All right, so let's do another one. 4 square root 3. All right, so 4 was allowed to leave the party because it started off as a pair. Originally 4 was in the party at 16. That's how it was, right? Because 4 times 4 is 16. Square root of 16 is 4. That's why it was able to leave. All right, 3 was not allowed to leave because it didn't have a pair, didn't have a match, didn't have someone to go with, right? So if I'm working backwards here, I want to put this 4 back under the radical, right? So to put it back under the radical, that means that there was 2 4s. So it was 4 times 4, right? So I also have that 3 that was stuck in there. So that 3 is still there too, right? So now I can multiply these together and find out my original answer. 3 times 4 is 12. 12 times 4 is 48. So that, my original answer was 48. That was my original problem. Okay? All right, try these ones down here on your own, right? So remember, you're putting this back inside the radical. So like this one, you're putting this 3 back inside the radical. So you're going to have to add 2 3s there, right? And then multiply them all together to get our original number. Try these ones on your own. Go ahead and pause the video. Try them on your own. And then unpause it when you're done, and we'll go on to see what we do with variables. Okay, so simplifying radicals with monomials, that just means variables with exponents, all right? That's what that monomial means. All right, what we're going to do is we're going to factor. We're going to expand our monomials, just like how we did with exponents. We're going to expand them out, all right? And then we're going to circle our pairs. We're going to circle our pairs. We're going to circle our pairs. They are allowed to leave the party because they were perfect squares. Right? Just like how we just did up with the numbers, we can do the same thing with variables, right? All right, squares, all right? Something non-pairs are going to stay under the radical or inside the radical. So anything that doesn't have a pair is going to stay under. All right, so let's think about this one. X to the 4th power, what does that mean? Well, that means that it's x times x times x times x. All right, then I would go through there and I would look for pairs, right? So I see I have a pair of x's here and a pair of x's here. So both of these things can come outside the radical, right? So I'm pulling out 2 pairs, so that means my answer would be x squared, right? Because I'm pulling out 2 pairs of x's. All right, so what if I had x to the 5th? Well, x to the 5th means that there's 5 x's, right? 1, 2, 3, 4, 5. I have 5 x's. Okay, so that means I can find my pair. So I see I have 1 pair there and another pair there. So both of these pairs can get pulled out, right? So I'm going to have x, and I'm pulling out 2 pairs. And I have 1 pair, or one that doesn't have a pair, and that's going to be stuck inside. So this is my answer, x squared to the square root of x. Okay? All right, go ahead, try these 2 on your own. Go ahead and pause the video, try those 2 on your own. All right, so let's put it all together. Let's do one of these together. All right, let's do this one on the right because that's a crazy hard one. All right, 180. I got to break down 180. What can I break 180 down into? Well, I could do 2 times 90, right? 2 I can't break down anymore, but 90 I can. 90 I can do 9 and 10, right? 9 I can break down into 3 and 3. 10 I can break down into 5 and 2, right? So now I have all of my prime numbers, right? I have all my prime numbers. I have a 2, I got a 3, I got a 3, I got a 5, and I got another 2. Okay, so I'm going to rewrite that under my radical. So I see there's a 2 here. I don't want to forget about that 2 in front. And then my square root. And then I see I have 2 2's, so 2 times 2. And I got 2 3's, 3 times 3. And I got a 5, so it times 5. Okay? So now I can find my pairs, right? So what pairs do I have? I have a pair of 2's and I got a pair of 3's. So both of those things can get pulled out. So when I pull those out, I'm going to have this original 2 times my pair of 2's that are coming out times 3, right? And what's stuck inside? Well, what's stuck inside is that 5 because it didn't have a pair. All right, so now I can multiply these. 2 times 2 is 4. 4 times 3 is 12. So I'm left with 12. And on the inside here, I still have that 5. Right? All right, but this one also has variables. So x to the 4th means that there's 4 x's. How many pairs would I have? Well, I have 1 pair, 2 pairs, right? So that means I can pull out 2 pairs of x. I got a y. Y doesn't have a pair. It's just 1 y. So that 1 y would stay there. I get z to the 3rd. That means that there's 3 z's. I have 1 pair of z's. So 1 z could come outside. 1 z is going to stay inside. And then that is my final answer. All All right, so that's what we do with radicals. Make a factor tree, and we're finding our pairs. Pairs can come outside the radical, everything else stays. See you next time.